Isaac Newton, a man who looked at a falling apple and saw the invisible threads that hold the entire universe together. Tonight, we're going to see the world through his eyes and discover how 3 simple laws changed everything we thought we knew about motion, force, and reality itself. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the elegant mathematics that govern everything from the smallest atom to the largest galaxy. There's absolutely no problem if you doze off midway through this exploration. Let your thoughts float through the cosmic machinery that Newton first revealed to humanity. If you find comfort in these gentle journeys through science, I'd be grateful if you'd consider subscribing and liking this video. Your support helps me reach that first 1,000 subscribers and continue creating these thoughtful explorations of the natural world. I'd love to know where you're listening from tonight. Feel free to comment your time and location below. Are you watching the stars emerge in your corner of the world? Perhaps it's morning where you are, with sunlight streaming through your window. There's something beautifully fitting about discussing Newton's laws while we're all scattered across different time zones. Each of us held to the Earth by the same gravitational force he first described. As we are featuring great comments made on our videos every day, tonight we are featuring Olive Hello. Seems like you considered watching one of our videos early in the morning. Feel free to drop one once you are done watching this video. Let's begin. Imagine you're sitting quietly, perhaps with a warm cup of tea, feeling the weight of your body against your chair. That sensation, that gentle pressure you feel, is gravity at work. But here's what makes this truly extraordinary. That same force pulling you down is identical to the force that keeps the moon circling Earth, that guides planets in their orbits, that shapes the very structure of galaxies across the cosmos. Isaac Newton was the first person in human history to realize this profound truth. And tonight, we're going to discover exactly how he did it. Imagine living in a world where motion was a mystery, where objects fell and no one could explain why, where the planets wandered across the sky according to patterns that seemed magical rather than mathematical. This was the world Newton inherited, a world where the heavens and earth seemed to operate by completely different rules, where philosophers debated whether a cannonball and a feather would fall at the same rate, but no one had the tools to find out for certain. But Newton possessed something extraordinary, not just intelligence, though he had that in abundance. He possessed a way of seeing that cut through centuries of confusion and revealed the elegant simplicity hiding beneath apparent chaos. He looked at the world and saw not separate phenomena, but a unified system governed by mathematical laws so precise they could predict the return of comets and the timing of eclipses with breathtaking accuracy. We're going to explore the 3 laws that Newton formulated. Laws so fundamental, they're still taught in every physics classroom around the world. Laws that launched the scientific revolution and made possible everything from space travel to the smartphone in your pocket. But more than that, we're going to understand how these laws revealed something profound about the nature of reality itself. The story begins with a question that seems almost childishly simple. Why do things move the way they do? It's a question humans had been asking for thousands of years. Ancient Greek philosophers thought heavy objects naturally fell faster than light ones. Medieval scholars believed objects moved because they had an innate desire to reach their proper place in the cosmic order. But Newton approached this question with a revolutionary tool: mathematics. He realized that motion wasn't about desire or natural tendencies. Motion was about forces, and forces, he discovered, followed precise mathematical relationships that could be expressed in elegant equations. These weren't just descriptions of how things moved. They were the underlying rules that determined how everything in the universe must move. Let's begin with Newton's first law, though he didn't call it that. He called it the law of inertia, and it completely overturned how humans thought about motion. The law states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This might sound obvious to us now, but in Newton's time, this was revolutionary thinking. Before Newton, people believed that objects naturally came to rest. If you rolled a ball across the ground, it would eventually stop, and scholars thought this happened because rest was the ball's natural state. But Newton realized something profound. The ball doesn't stop because it wants to rest. It stops because something is acting on it. Friction from the ground, resistance from the air, tiny, invisible forces that gradually drain away its motion. Picture a perfectly smooth ice rink stretching infinitely in all directions. No air resistance, no friction, nothing to interfere with motion. If you gave a hockey puck a gentle push on this imaginary surface, Newton's first law tells us something amazing would happen. That puck would glide forever, maintaining exactly the same speed and direction you gave it until the end of time. This isn't science fiction. This is the fundamental nature of motion itself. But here's where it gets truly mind-bending. You're sitting still right now, reading these words. According to Newton's first law, you're actually moving at tremendous speed. Earth is spinning on its axis at over 1,000 miles per hour at the equator. Earth is orbiting the Sun at nearly 70,000 miles per hour. Our entire solar system is racing through the galaxy at 500,000 miles per hour, and our galaxy itself is hurtling through space at over 1,000,000 miles per hour. Yet you feel perfectly at rest. Why? Because there's no external force acting on you to change your motion relative to Earth. You and the planet are moving together through space like passengers on a cosmic ship. Newton's first law explains why you don't feel this incredible motion. Motion isn't absolute, it's relative. What matters isn't how fast you're moving, but whether that motion is changing. This insight led Newton to understand something that would revolutionize physics. There's no such thing as absolute rest or absolute motion. These concepts only make sense relative to something else. You're at rest relative to your chair, but in motion relative to the sun. The sun is at rest relative to the other stars in our local neighborhood, but in motion relative to the center of our galaxy. Motion and rest are not fixed properties of objects. They're relationships between objects. Newton's first law also revealed why space travel is possible. Once a spacecraft escapes Earth's gravitational pull and air resistance, it can coast through the vacuum of space for years without using any fuel. The Voyager probes, launched in the 1970s, are still racing away from our solar system today, their motion unchanged since they left Earth's influence decades ago. They're living proof of Newton's first law, carrying human messages into the cosmic deep. But inertia isn't just about objects in motion, it's also about objects at rest. That feeling of being pressed back into your seat when a car accelerates, or being thrown forward when it brakes suddenly, that's inertia at work. Your body wants to maintain its current state of motion, but the car is changing that motion. The result is the sensation of force pushing or pulling you. Think about a magician pulling a tablecloth out from under dishes on a table. If done quickly enough, the dishes remain in place, because their inertia keeps them at rest while the cloth slides away beneath them. This isn't magic. It's Newton's first law in action. The dishes stay put because no significant force acts on them in the horizontal direction. Newton's first law also explains why seatbelts save lives. In a car crash, the vehicle suddenly stops, but your body, following the law of inertia, continues moving forward at the car's original speed. Without a seatbelt to provide the external force needed to change your motion, you would continue through the windshield. The seatbelt applies the force necessary to bring your body to rest along with the car. This law extends far beyond everyday experiences. It governs the motion of planets, stars, and galaxies. It explains why comets follow predictable orbits and why satellites can maintain stable paths around Earth. Every object in the universe, from the smallest grain of dust to the largest galaxy, obeys this fundamental principle. But Newton didn't stop with the first law. He realized that understanding motion required more than just knowing that objects resist changes to their motion. He needed to understand exactly how motion changes when forces are applied. This led him to formulate his second law, which is perhaps the most important equation in all of physics. Newton's second law can be expressed in a simple equation. Force equals mass times acceleration. Don't let the simplicity fool you. This equation contains within it the secret to understanding virtually every form of motion in the universe. It tells us that the force acting on an object is directly proportional to how quickly that object's motion changes, and inversely proportional to the object's mass. Let's unpack this carefully, because this law governs everything from the flight of a baseball to the orbit of planets. When you push on something, you're applying a force. The harder you push, the greater the force. But the effect of that force depends on two things: how much mass the object has, and how quickly you want to change its motion. Mass is often confused with weight, but they're different concepts. Mass is the amount of matter in an object, a fundamental property that never changes regardless of location. Weight is the force that gravity exerts on that mass, and it can vary depending on where you are. An astronaut floating in space is weightless, but they still have the same mass they had on Earth. The relationship between force, mass, and acceleration reveals something beautiful about the universe. It takes the same force to accelerate a 1 kilogram object at 1 meter per second squared as it does to accelerate a 2 kilogram object at half a meter per second squared. The universe maintains this precise mathematical relationship in every interaction, from colliding atoms to merging galaxies. This law explains why it's harder to push a full shopping cart than an empty one. The full cart has more mass, so the same force produces less acceleration. It explains why race cars are built to be as light as possible while still maintaining structural integrity. Less mass means the same engine force produces greater acceleration. Newton's second law also reveals why different objects fall at the same rate in a vacuum, despite having different masses. This was one of Galileo's great insights, which Newton's laws helped explain. In a vacuum, the only force acting on a falling object is gravity. Heavier objects experience more gravitational force, but they also have more mass to accelerate. These two effects exactly cancel out, resulting in the same acceleration for all objects regardless of their mass. Think about this for a moment. A feather and a hammer dropped on the moon, where there's no air resistance, will hit the ground at exactly the same time. This isn't intuitive, based on our everyday experience, but it reveals the elegant mathematical precision with which the universe operates. The force of gravity is perfectly calibrated to the mass it acts upon, creating a universal acceleration that's the same for all objects. Newton's second law also governs the motion of planets around the Sun. The gravitational force between the Sun and a planet provides exactly the right amount of centripetal force to keep the planet in orbit. If the force were too weak, the planet would fly off into space. If it were too strong, the planet would spiral into the Sun. But nature has calibrated these forces with mathematical precision, creating stable orbits that can persist for billions of years. This law extends to every scale of the universe. It governs the motion of electrons around atomic nuclei, the rotation of hurricanes, the collision of galaxies, and the expansion of space itself. Every acceleration, every change in motion throughout the cosmos follows this same fundamental relationship between force, mass, and acceleration. As we settle deeper into this exploration of Newton's revolutionary insights, we begin to see how these laws reveal the universe as a vast, interconnected machine operating according to precise mathematical principles. What seemed like chaos to earlier generations revealed itself to Newton as elegant order, predictable and beautiful in its simplicity. But we've only begun to explore the profound implications of Newton's work. His third law will reveal an even deeper truth about the nature of forces and interactions, showing us that every action in the universe creates an equal and opposite reaction, binding all matter and energy into a cosmic dance of mutual influence and response. But before we delve into that cosmic dance, let's pause and truly appreciate what Newton's second law reveals about the fabric of reality itself. When you gently push a door open, when a bird beats its wings against the air, when stellar winds carry particles across interstellar space, the same mathematical relationship governs every interaction. The universe operates like a vast calculator, continuously computing the precise acceleration that results from every force acting on every piece of matter. This computational aspect of reality becomes even more remarkable when we consider that Newton discovered these laws without modern technology. No computers, no sophisticated measuring instruments, no high-speed cameras to capture motion. He used pure mathematical reasoning, careful observation, and profound intuition to uncover principles that we now know govern everything from quantum particles to galactic clusters. Think about the elegance of this discovery. Newton realized that you could predict the future motion of any object if you knew three things: its current position, its current velocity, and all the forces acting upon it. This was revolutionary. For the first time in human history, the future became calculable, not just approximately, but with mathematical precision. This predictive power transformed our relationship with the natural world. Before Newton, events like eclipses and comet returns were mysterious, often interpreted as omens or divine interventions. After Newton, they became celestial clockwork, predictable centuries in advance. Edmund Halley used Newton's laws to predict that the comet now bearing his name would return every 76 years. When it appeared exactly as predicted, it provided stunning confirmation of Newton's mathematical description of the universe. The implications rippled far beyond astronomy. Engineers could now calculate exactly how much force was needed to build bridges that wouldn't collapse, to design machines that would work reliably, to plan construction projects with confidence. The Industrial Revolution became possible because Newton had given humanity the mathematical tools to harness forces with precision. But Newton's second law also revealed something deeply philosophical about the nature of causation itself. Every acceleration, every change in motion requires a cause. Objects don't simply decide to speed up or slow down. Something must push or pull them. This insight established a fundamental principle that would guide scientific thinking for centuries. Every effect has a cause, and that cause can be understood through mathematical analysis. Consider how this applies to your own body right now. As you breathe, your diaphragm creates pressure differences that cause air to flow into and out of your lungs. When your heart beats, it applies force to blood, accelerating it through your circulatory system. When you blink, tiny muscles apply forces to your eyelids, changing their motion in precise coordination. Every biological process, every chemical reaction, every molecular interaction follows Newton's mathematical laws. This universality is breathtaking. The same equation that describes a baseball flying through the air also describes the motion of planets, the behavior of tides, the oscillation of pendulums, and the trajectory of spacecraft. Newton had discovered that the universe speaks a single mathematical language, and he had learned to translate that language into human understanding. The second law also illuminated the relationship between energy and motion in ways that would later inspire entire fields of physics. When you apply a force to accelerate an object, you're transferring energy to it. The faster the object moves, the more kinetic energy it possesses. This energy doesn't disappear when the object slows down. It transforms into heat, sound, or other forms of energy, but the total amount remains constant. Newton's work laid the groundwork for understanding energy conservation, one of the most fundamental principles in all of science. But perhaps most remarkably, Newton's second law revealed that mass is not just the amount of matter in an object. Mass is resistance to acceleration. The more mass something has, the more force you need to change its motion. This insight would later prove crucial to Einstein's theories of relativity, where mass and energy reveal themselves as different aspects of the same fundamental quantity. As we contemplate these profound insights, we begin to appreciate why Newton's laws represented such a monumental leap in human understanding. They didn't just describe how things move. They revealed the underlying logic of the physical world, showing that beneath apparent complexity lies elegant mathematical simplicity. Yet Newton wasn't finished. His third law would reveal an even more profound truth about the interconnected nature of reality. This law would show that forces never act in isolation, that every push creates a pull, that every action generates an equal and opposite reaction. It would demonstrate that the universe is not a collection of separate objects, but a unified system where every part influences every other part through invisible threads of force and motion. Newton's third law states that for every action, there is an equal and opposite reaction. But this simple statement contains within it a truth so fundamental that it governs everything from the smallest atomic interactions to the largest cosmic phenomena. When you walk forward, you push backward against the ground with your feet. The ground pushes forward against you with exactly equal force, propelling you ahead. When a rocket engine fires, hot gases rush out the back, and the rocket experiences an equal force pushing it forward into space. This law reveals that forces always come in pairs. You cannot have a push without a pull, an attraction without a repulsion, an action without a reaction. Every force in the universe exists as part of a matched set, each member of the pair equal in magnitude but opposite in direction. This isn't just a curious fact about physics. It's a fundamental principle that makes the universe stable and predictable. Consider what happens when you lean against a wall. You apply a force to the wall, pushing against it. Simultaneously, the wall applies an equal force back against you, preventing you from falling forward. If the wall weren't there to provide that reaction force, you would topple over. The wall doesn't choose to push back against you. It must push back because Newton's third law allows no exceptions. This principle explains how birds fly through the air. When a bird's wing pushes down and back against the air pushes up and forward against the wing with equal force. The downward component creates lift, while the forward component provides thrust. The bird moves through the sky not by violating the laws of physics, but by using them with exquisite precision. The same principle governs swimming. When a swimmer pushes water backward with their hands and feet, the water pushes the swimmer forward with equal force. Fish propel themselves through water using this same fundamental interaction, their fins and tails creating action-reaction pairs that generate motion with remarkable efficiency. Newton's third law also explains how wheels work. When a car's tires push backward against the road pushes forward against the tires with equal force, moving the car ahead. This is why cars can't accelerate on ice or loose sand. Without sufficient friction to create the reaction force, the wheels simply spin without generating forward motion. But the implications extend far beyond everyday mechanics. This law governs the motion of planets around stars, stars around galactic centers, and galaxies through the cosmic web. When Earth orbits the Sun, Earth pulls on the Sun with gravitational force, and the Sun pulls back on Earth with exactly equal force. The Sun is much more massive than Earth, so it doesn't move very much in response to Earth's pull. but it does move slightly. In fact, astronomers use this principle to detect planets around distant stars by observing the tiny wobbles these planets create in their host star's motion. The law reveals something profound about the nature of gravity itself. Gravity is not something that large objects do to smaller ones. It's a mutual interaction. You pull on Earth with exactly the same gravitational force that Earth pulls on you. The reason you fall toward Earth rather than Earth falling toward you is simply that Earth has enormously more mass, so the same force produces much less acceleration in Earth than in you. This mutual nature of forces extends to every interaction in the universe. When atoms bond together to form molecules, each atom pulls on the others, and the others pull back with equal force. When light pushes against objects creating radiation pressure, those objects push back against the light with equal force. When magnetic fields interact, each field experiences forces equal and opposite to those it creates in other fields. Newton's third law also illuminates the principle of momentum conservation. When two objects interact, the forces they exert on each other are equal and opposite, so the momentum one object gains, the other must lose. The total momentum of the system remains constant. This principle governs everything from billiard ball collisions to the formation of galaxies from primordial gas clouds. Think about what happens when you jump. You push down against the ground, and the ground pushes up against you with equal force. But why don't you and the Earth move equal distances in opposite directions? The answer lies in Newton's second law working together with the third law. The forces are equal, but Earth has vastly more mass than you, so the same force produces much less acceleration in Earth. You leap upward while Earth recoils downward by an almost imperceptibly tiny amount. This interplay between Newton's laws reveals the universe as an intricate system of mutual influences and responses. Nothing moves in isolation. Every motion creates countermotions. Every force generates counterforces. Every action ripples through the cosmic web of interactions that connects all matter and energy. The third law also explains how rockets work in the vacuum of space, where there's nothing to push against. Early critics of space travel argued that rockets couldn't work in space because there was no air to push against. But Newton's third law reveals this thinking as flawed. Rockets work by expelling mass at high velocity. The expelled mass carries momentum in one direction, so the rocket must gain equal momentum in the opposite direction. No external medium is required. The rocket carries its own reaction mass in the form of fuel. This principle governs the motion of every spacecraft humanity has ever launched. From the first satellites to interplanetary probes to crewed missions to the moon and space stations, all rely on Newton's third law for propulsion. The elegant mathematics Newton discovered 3 centuries ago continue to guide our exploration of the cosmos. As we reflect on these 3 laws together, we begin to see how they form a complete description of motion and force. The first law tells us that objects resist changes to their motion. The second law tells us exactly how motion changes when forces are applied. The third law tells us that forces always come in equal and opposite pairs. Together, these principles create a mathematical framework that describes the behavior of everything, from subatomic particles to galaxy clusters. But Newton's laws revealed something even more profound than the mechanics of motion. They showed that the universe operates according to comprehensible mathematical principles. This was a revolutionary idea. Before Newton, many people believed that natural phenomena were fundamentally mysterious, beyond human understanding. Newton demonstrated that careful observation combined with mathematical reasoning could unlock the deepest secrets of nature. This insight launched the scientific revolution and continues to guide scientific inquiry today. Every time we send a probe to Mars, design a new building, or engineer a medical device, we're applying principles that Newton first articulated. His laws didn't just describe the world as it was in the 17th century. They revealed timeless truths about the structure of reality itself. Yet as we delve deeper into Newton's revolutionary framework, we encounter something truly extraordinary. These laws don't just describe motion, they reveal the universe as a vast, interconnected symphony where every note resonates with every other note. When you tap your finger on a table, that tiny action sends vibrations through the wood, into the air, down through the floor, and ultimately affects every particle in the observable universe, however minutely. This interconnectedness becomes even more profound when we consider how Newton's laws govern the dance of celestial bodies. The Moon doesn't simply orbit Earth in isolation. Its gravitational pull creates our ocean tides, affecting every drop of water on our planet's surface. Meanwhile, Earth's gravity tugs back on the Moon, gradually slowing its rotation and pulling it slightly farther away each year. This cosmic choreography has been unfolding for billions of years, each movement precisely determined by the mathematical relationships Newton first described. Picture the solar system as Newton saw it, not as a collection of separate worlds, but as a single, unified mechanism. The Sun's immense gravitational field reaches out across billions of miles, holding each planet in its designated orbital path. Jupiter's massive presence influences the orbits of asteroids and comets, occasionally flinging them toward the inner solar system. Saturn's rings maintain their delicate structure through gravitational resonances with its moons. Every celestial body influences every other celestial body in an intricate web of forces and counterforces. But Newton's vision extended even beyond our solar system. He realized that the same laws governing a falling apple must also govern the motion of distant stars. This was a breathtaking leap of imagination. Newton looked up at the night sky and understood that those tiny points of light were actually enormous suns, perhaps with their own families of planets, all following the same mathematical principles that governed motion here on Earth. This universality of physical law was perhaps Newton's greatest insight. The universe doesn't operate according to different rules in different places or at different scales. The force that makes your coffee cup fall when you accidentally knock it off the table is the same force that holds galaxies together across millions of light years. The mathematics that describe a child's swing in a playground also describe the oscillations of massive stellar systems. Consider how this applies to the very atoms that make up your body. The electrons orbiting atomic nuclei follow paths determined by forces that obey Newton's laws, modified by quantum mechanical effects he couldn't have imagined. The chemical bonds holding your DNA together exist because of electromagnetic forces that create action-reaction pairs at the molecular level. Every breath you take involves millions of gas molecules bouncing off the walls of your lungs, each collision governed by Newton's third law. This microscopic dance of forces extends upward through every scale of organization. Cells push and pull against each other as they divide and grow. Muscles contract by billions of molecular motors pulling on protein filaments. Your heart beats because electrical forces cause muscle fibers to shorten in coordinated waves. Blood flows through your circulatory system, driven by pressure differences that follow the same principles governing fluid motion everywhere in the universe. Newton's laws also illuminate the profound relationship between structure and motion in the natural world. Consider how a bird's wing generates lift. The curved shape of the wing forces air to move faster over the top surface than the bottom surface. This creates a pressure difference that pushes the wing upward. But this is only possible because air molecules obey Newton's laws, accelerating when forces act upon them, responding to pressure gradients with predictable motions. The same principles govern the formation of weather patterns. Uneven heating of Earth's surface creates pressure differences in the atmosphere. Air accelerates from high-pressure regions toward low-pressure regions, but Earth's rotation deflects these flows, creating the swirling patterns we see in hurricanes and jet streams. Every cloud, Every breeze, every thunderstorm represents Newton's laws operating on a massive scale. Ocean currents follow similar patterns, driven by temperature differences, salinity variations, and the Coriolis effect created by Earth's rotation. The Gulf Stream carries warm water northward along the Atlantic coast, moderating the climate of entire continents. These currents transport not just heat, but nutrients, marine life, and even human vessels, all following paths determined by the interplay of forces Newton first mathematically described. Even the solid Earth beneath your feet responds to forces in ways Newton's laws predict. Tectonic plates drift across the planet's surface, driven by convection currents in the molten mantle below. When these plates collide, mountains rise. When they separate, new ocean floor forms. Earthquakes occur when accumulated stress exceeds the strength of rock, releasing energy in seismic waves that travel through the planet at speeds determined by the density and elasticity of Earth's interior. But perhaps nowhere do Newton's laws reveal their elegance more clearly than in the realm of engineering and technology. Every bridge spans its river because engineers calculated exactly how much force the structure must withstand and designed supports capable of providing equal and opposite reactions. Every airplane flies because its wings are shaped to create pressure differences that generate lift forces greater than the aircraft's weight. The smartphone in your pocket represents thousands of applications of Newton's laws. The tiny vibrating motor that provides haptic feedback operates by electromagnetic forces, creating rapid accelerations in a small mass. The gyroscope that detects when you rotate the device relies on the tendency of spinning objects to maintain their orientation in space, a consequence of Newton's first law. Even the touchscreen responds to the electrical forces between your finger and the display surface. Space exploration provides perhaps the most dramatic demonstrations of Newton's laws in action. When engineers plan a mission to Mars, they must calculate trajectories months or years in advance, accounting for the gravitational influences of Earth, the Moon, the Sun, and even Jupiter. The spacecraft follows a path through space determined entirely by these gravitational forces, arriving at its destination with pinpoint accuracy after traveling hundreds of millions of miles. Consider the elegant mathematics involved in such a journey. The spacecraft begins by accelerating away from Earth, but it never truly escapes Earth's gravitational influence. Instead, it follows a complex trajectory that balances Earth's pull against the Sun's much stronger but more distant gravitational field. As it travels toward Mars, the spacecraft's path curves continuously, responding to the combined gravitational forces of all the planets in the solar system. This interplanetary navigation represents one of humanity's greatest intellectual achievements, made possible by Newton's mathematical description of force and motion. The same equations that describe a bouncing ball also guide robotic explorers across the solar system, allowing us to land rovers on Mars, orbit Saturn's moons, and fly past Pluto with breathtaking precision. But Newton's laws also reveal something profound about the nature of time itself. In Newton's universe, time flows uniformly everywhere, providing an absolute framework against which all motion can be measured. This conception of time as a universal constant seemed obviously correct for centuries, until Einstein showed that time itself can stretch and compress depending on gravity and motion. Yet even Einstein's revolutionary insights built upon Newton's foundation. The mathematical tools Newton developed to describe motion through space became the starting point for understanding motion through spacetime. Newton's laws remain perfectly accurate for describing the motion of objects moving much slower than the speed of light in gravitational fields, much weaker than those near black holes. This enduring relevance of Newton's work speaks to the profound nature of his insights. He didn't just describe the motion he could observe in his own time. he uncovered fundamental principles that govern the behavior of matter and energy throughout the universe. Every technological advancement from the Industrial Revolution to the space age has relied on the mathematical framework Newton established. As we sit here contemplating these cosmic truths, we're experiencing Newton's laws firsthand. Gravity holds you in your chair, friction keeps your feet from sliding across the floor, and electromagnetic forces bind the atoms of your body together. Your breathing, your heartbeat, your very thoughts depend on the precise interplay of forces that Newton first learned to describe mathematically. The elegance of this mathematical description continues to inspire scientists and engineers today. When researchers design new materials at the atomic level, they apply Newton's laws to understand how individual atoms will behave under different conditions. When astronomers discover new exoplanets orbiting distant stars, they use Newton's mathematics to determine orbital periods and planetary masses. Even in the quantum realm, where particles behave according to probabilities rather than certainties, Newton's classical concepts of force and motion provide essential insights. Quantum mechanics describes the probability that a particle will be found at different locations. But when measurements collapse these probabilities into definite outcomes, the resulting motion follows Newton's laws. This seamless connection between classical and quantum physics reveals something beautiful about the structure of scientific knowledge. Each new discovery doesn't replace previous understanding, but builds upon it, extending our comprehension into new realms, while preserving the elegant truths earlier generations uncovered. Newton's laws also illuminate the relationship between simplicity and complexity in nature. The equations themselves are remarkably simple, yet they generate behaviors of incredible richness and variety. A double pendulum, governed by nothing more than gravity and Newton's laws, can exhibit chaotic motion so complex that its long-term behavior becomes unpredictable. Weather systems, stock markets, and ecological populations all display similar complexity, emerging from relatively simple underlying rules. This emergence of complexity from simplicity reflects a deep principle about how the universe organizes itself. Simple mathematical relationships, repeated and combined across multiple scales, create the rich tapestry of phenomena we observe in nature. Newton's laws provide the fundamental grammar from which the universe constructs its infinite variety of motions and interactions. As we prepare to explore even deeper implications of Newton's revolutionary insights, we begin to appreciate how profoundly these laws have shaped not just our understanding of the physical world, but our entire conception of what it means to live in a universe governed by mathematical principles. The story of how Newton discovered these laws, and how they continue to guide our exploration of reality, reveals something essential about the human capacity to comprehend the cosmic order through careful observation and mathematical reasoning. The story of how Newton arrived at these profound insights is itself a testament to the power of mathematical thinking. Picture a young man in his early 20s, sitting in his mother's garden in Woolsthorpe, watching an apple fall from a tree. Most people would see nothing more than fruit dropping to the ground. But Newton saw something extraordinary. He saw the same force that pulled the apple downward also reaching across the vast emptiness of space to hold the moon in its orbit around Earth. This moment of insight didn't happen suddenly. Newton had been wrestling with the problem of planetary motion for years, trying to understand why planets moved in elliptical orbits rather than flying off into space or spiraling into the sun. The mathematics were fiendishly complex, involving what we now call calculus, which Newton had to invent just to solve these problems. But the apple provided the crucial intuition. If gravity could reach from Earth's center to its surface, pulling objects downward, why couldn't it reach much farther? Perhaps the same force extended all the way to the moon, constantly pulling our satellite toward Earth. The moon doesn't fall into Earth because it's also moving sideways fast enough that as it falls, Earth's surface curves away beneath it. The moon is literally falling around Earth in an eternal dance of motion and force. This realization led Newton to one of the most elegant insights in the history of science. He calculated that if you could somehow launch a cannonball fast enough from a mountaintop, it would orbit Earth just like the Moon, too slow, and it would crash into the ground, too fast, and it would escape into space. But at exactly the right speed, it would fall continuously around Earth's curved surface, never getting closer or farther away. This thought experiment revealed that orbital motion isn't fundamentally different from the motion of falling objects. Both are governed by the same gravitational force, the same mathematical relationships. A satellite orbiting Earth experiences the same acceleration toward our planet's center as an apple falling from a tree. The only difference is that the satellite also has sideways velocity that keeps it from hitting the ground. Newton's mathematical analysis revealed something even more profound. The force of gravity follows what we now call an inverse square law. Double the distance between two objects, and the gravitational force between them becomes 4 times weaker. Triple the distance, and the force becomes 9 times weaker. This precise mathematical relationship emerged from Newton's calculations of planetary orbits and his analysis of falling objects on Earth. Consider the elegant precision of this law. Earth pulls on the Moon with gravitational force, but if the Moon were somehow moved to twice its current distance, Earth's gravitational influence would become exactly 1/4 as strong. This isn't an approximation or a rough estimate. It's a precise mathematical relationship that governs every gravitational interaction in the universe. This inverse square law explains why gravity seems so strong on Earth's surface, but becomes negligible in the depths of space. Astronauts orbiting just a few hundred miles above Earth experience nearly the same gravitational force as people on the ground. But by the time you travel to the Moon, Earth's gravitational pull has weakened dramatically. The mathematical precision of this relationship allows us to calculate exactly how much fuel a spacecraft needs to escape Earth's gravitational well and reach other planets. Newton's work also revealed why Kepler's laws of planetary motion worked so well. Johannes Kepler had discovered through careful observation that planets move in elliptical orbits, sweeping out equal areas in equal times, with orbital periods related to their distances from the Sun by a precise mathematical formula. But Kepler didn't know why these laws worked. Newton showed that they were inevitable consequences of gravity following an inverse square law. This connection between Newton's force law and Kepler's kinematic descriptions provided powerful confirmation that Newton had indeed discovered the fundamental principles governing motion throughout the solar system. The same mathematics that explained why apples fall also explained why Mars takes longer to orbit the Sun than Earth, why comets follow elongated elliptical paths, and why Jupiter's moons dance around their giant planet in perfect mathematical harmony. But Newton's insights extended far beyond our solar system. He realized that every star in the night sky must also follow these same laws. Binary stars orbit around their common center of mass according to the same principles that govern planetary motion. Globular clusters, containing hundreds of thousands of stars, maintain their spherical shapes because each star's motion is determined by the gravitational forces exerted by all the others. The mathematical tools Newton developed to solve these problems revolutionized not just physics, but all of science. Before Newton, natural philosophy was largely descriptive, cataloging observations without providing predictive mathematical frameworks. After Newton, science became quantitative, capable of making precise predictions that could be tested against observation. This transformation had profound implications for human civilization. Engineers could now calculate the forces acting on structures before building them, ensuring that bridges would support their intended loads and buildings would withstand expected stresses. The same mathematical principles that governed falling apples could be applied to designing machines, optimizing mechanical systems, and understanding the behavior of materials under stress. Newton's laws also illuminated the relationship between force and energy in ways that would later inspire entire fields of physics. When you lift an object against gravity, you're doing work, transferring energy to the object by applying force through a distance. This energy doesn't disappear when you release the object. It transforms into kinetic energy as the object falls, then into heat and sound when the object hits the ground. This principle of energy conservation, implicit in Newton's laws but not fully developed until later, revealed another fundamental truth about the universe. Energy cannot be created or destroyed, only transformed from one form to another. The energy stored in a compressed spring, the kinetic energy of a moving car, the potential energy of water behind a dam, all represent different manifestations of the same underlying quantity. Consider how this applies to the motion of planets around the Sun. As a planet moves closer to the Sun in its elliptical orbit, it speeds up, converting gravitational potential energy into kinetic energy. As it moves farther away, it slows down, converting kinetic energy back into potential energy. The total energy remains constant throughout the orbit, creating the stable, predictable motion that has persisted for billions of years. This conservation principle extends to every scale of the universe. In chemical reactions, the bonds between atoms store potential energy that can be released when those bonds break and new ones form. In nuclear reactions, tiny amounts of mass convert into enormous amounts of energy according to Einstein's famous equation. Even in the quantum realm, where particles pop in and out of existence, energy conservation provides an absolute constraint on what can happen. Newton's mathematical framework also revealed something profound about the nature of scientific prediction. Given complete information about the position and velocity of every particle in a system, along with knowledge of all the forces acting on those particles, Newton's laws allow you to calculate the future state of the system with perfect accuracy. This deterministic view of nature suggested that the universe operates like a vast, complex clockwork mechanism. This mechanical worldview had enormous influence on philosophy, literature, and human self-understanding. If the motion of planets could be predicted centuries in advance using mathematical equations, perhaps human behavior, biological processes, and social phenomena might also follow discoverable laws. The success of Newtonian mechanics inspired scholars in many fields to search for the mathematical principles underlying their own domains of study. Yet Newton himself remained humble about the scope of his achievements. He famously wrote that he felt like a child playing on the seashore, finding a smoother pebble or prettier shell than ordinary, while the great ocean of truth lay undiscovered before him. This humility reflected his awareness that even his revolutionary insights represented only the beginning of humanity's quest to understand the natural world. Modern science has indeed discovered phenomena that Newton couldn't have imagined. Einstein's relativity revealed that space and time themselves can bend and warp. Quantum mechanics showed that particles exist in superpositions of states until measured. Chaos theory demonstrated that even simple systems governed by Newton's laws can exhibit unpredictable behavior. Yet these discoveries didn't replace Newton's insights, but extended them into new realms. Newton's laws remain perfectly accurate for describing the motion of objects moving much slower than the speed of light in gravitational fields, much weaker than those near black holes. Every spacecraft we launch, every bridge we build, every machine we design relies on the mathematical framework Newton established. His laws continue to provide the foundation for engineering and technology throughout our civilization. The enduring power of Newton's work also lies in its revelation of the deep mathematical structure underlying physical reality. The universe doesn't just happen to follow mathematical patterns, it seems to be constructed from mathematical relationships. Numbers, equations, and geometric principles appear to be the fundamental building blocks from which all physical phenomena emerge. This mathematical nature of reality continues to astonish scientists and philosophers. Why should the universe be comprehensible to mathematical analysis? Why do simple equations describe complex phenomena with such precision? These questions point towards something profound about the relationship between human reasoning and the cosmic order. Newton's laws also demonstrate the cumulative nature of scientific knowledge. Each generation of scientists builds upon the insights of their predecessors, extending understanding into new territories while preserving the essential truths earlier generations discovered. Newton himself acknowledged this, writing that if he had seen farther than others, it was by standing on the shoulders of giants. The giants Newton stood upon included Galileo, who established that all objects fall at the same rate in a vacuum and discovered the moons of Jupiter; Kepler, who mapped the elliptical orbits of planets with mathematical precision; Descartes, who developed coordinate geometry and emphasized the importance of mathematical description in natural philosophy. Each contributed essential pieces to the puzzle that Newton assembled into a comprehensive theory of motion and force. But Newton's synthesis went far beyond simply combining earlier insights. He created entirely new mathematical tools, developed novel experimental techniques, and formulated principles of such generality that they continue to guide scientific research today. His work represents one of the greatest intellectual achievements in human history, comparable to the development of written language or the discovery of agriculture in its transformative impact on civilization. The story of Newton's discoveries also illustrates the importance of mathematical imagination in scientific progress. Newton didn't just observe falling apples and orbiting planets. He imagined cannonballs launched at incredible speeds, visualized forces extending across cosmic distances, and conceived of space as filled with invisible gravitational influences. These acts of imagination, guided by mathematical reasoning, allowed him to perceive patterns and relationships that pure observation alone could never reveal. This combination of imagination and mathematical rigor continues to characterize the most profound scientific discoveries. Einstein imagined riding alongside a beam of light to develop his theory of relativity. Darwin envisioned the branching tree of life to understand biological evolution. Mendeleev imagined the periodic patterns underlying chemical elements. In each case, mathematical or conceptual frameworks provided the tools for organizing and extending imaginative insights. Newton's work also demonstrates how scientific understanding deepens through the interplay between theory and experiment. His laws made precise predictions about planetary motions, projectile paths, and pendulum oscillations that could be tested against careful observations. When predictions matched observations with extraordinary accuracy, confidence in the theoretical framework grew. When discrepancies appeared, they pointed toward phenomena requiring deeper investigation. This process of prediction and testing created a feedback loop that continuously refined and extended scientific knowledge. Each successful prediction strengthened confidence in Newton's laws, while each new application revealed previously unknown aspects of natural phenomena. The mathematical framework became a lens through which investigators could perceive ever more subtle and complex patterns in the behavior of matter and energy. As we reflect on the profound implications of Newton's revolutionary insights, we begin to appreciate how completely they transformed human understanding of our place in the cosmos. Before Newton, Earth seemed like a special realm with its own unique laws, fundamentally different from the celestial sphere, where planets and stars moved according to mysterious principles. After Newton, Earth revealed itself as one planet among many, all governed by the same mathematical laws that operate throughout the universe. This cosmic perspective continues to shape how we understand ourselves and our relationship to the natural world. We are not separate from the universe, but part of it, made from the same matter, governed by the same forces, following the same laws that guide the motion of galaxies across billions of light years. The calcium in our bones was forged in the hearts of ancient stars. The water in our cells has been cycling through Earth's systems for billions of years. The energy powering our thoughts originated in nuclear reactions deep within the sun. Newton's laws provide the mathematical language for describing these cosmic connections. They reveal how forces ripple through space and time, connecting every particle to every other particle in an intricate web of influences and responses. When you take a step forward, that tiny action creates gravitational waves that propagate throughout the universe, carrying information about your motion to the most distant galaxies, however faintly. This interconnectedness becomes even more remarkable when we consider how Newton's laws govern the formation and evolution of cosmic structures. In the early universe, tiny density fluctuations grew under their own gravitational attraction, eventually collapsing to form the first stars and galaxies. These processes continue today as gas clouds condense to birth new stars, as galaxies merge and evolve, as the large-scale structure of the universe continues to develop according to the same mathematical principles Newton first articulated. The elegance of Newton's mathematical description also reflects something profound about the nature of beauty in science. The equations themselves possess an aesthetic quality that transcends their practical utility. There's something deeply satisfying about seeing complex phenomena explained by simple, elegant mathematical relationships. This beauty isn't merely decorative. It often points toward fundamental truth, suggesting that the universe possesses an underlying harmony that human minds can appreciate and understand. Yet perhaps the most remarkable aspect of Newton's legacy lies in how it continues to inspire new discoveries and applications. Every time engineers design a new spacecraft trajectory, every time physicists model the behavior of complex systems, every time students learn to analyze motion and force, they're participating in the ongoing development of insights that Newton first articulated centuries ago. The mathematical tools he created have been refined and extended, but their essential character remains unchanged. Differential equations still describe how quantities change over time. Vector analysis still provides the language for describing forces and motions in three-dimensional space. Conservation principles still constrain what can happen in physical interactions. These tools, born from Newton's analysis of falling apples and orbiting planets, now guide our exploration of everything from subatomic particles to the structure of space-time itself. This universality of Newton's mathematical framework reveals something extraordinary about the architecture of reality itself. Every interaction you experience, from the gentle pressure of air against your skin to the electromagnetic forces holding the atoms of your body together, follows the same fundamental principles that govern the dance of galaxies across cosmic time. The coffee cup resting on your table obeys the same laws that guide binary stars as they spiral around each other in distant stellar systems. Consider the profound implications of this unity. When Newton first realized that terrestrial and celestial phenomena followed identical mathematical relationships, he was revealing something deeper than just the mechanics of motion. He was uncovering evidence that the universe possesses an underlying logical structure, a cosmic grammar written in the language of mathematics that applies everywhere and at every scale. This mathematical consistency extends through dimensions of space and time that Newton could barely imagine. The same inverse square law that describes how gravitational force weakens with distance also governs how light spreads out from a source, how electric fields diminish around charged particles, and how the influence of magnetic fields decreases as you move away from their sources. This isn't coincidence. It reflects the geometric properties of three-dimensional space itself. Picture how this geometric principle manifests in your daily experience. When you move twice as far from a campfire, you receive 1/4 the heat. When you step back from a bright light, its intensity diminishes by exactly the same mathematical relationship. The sound from a speaker follows this same pattern, becoming 4 times quieter when you double your distance. These aren't separate phenomena requiring different explanations. They're all expressions of how influences propagate through the three-dimensional space we inhabit. Newton's insights also illuminate the profound relationship between symmetry and physical law. The mathematical relationships he discovered remain unchanged whether you're moving north or south, Whether you conduct your experiments on Monday or Friday, whether you're in London or Tokyo, this symmetry isn't merely convenient for scientists. It reflects something fundamental about the structure of space-time itself. This principle of symmetry extends to the very foundations of Newton's laws. The first law treats all directions equally. There's no preferred direction for motion in empty space, no cosmic up or down that objects naturally seek. The second law applies the same mathematical relationship between force, mass, and acceleration, regardless of which direction the force points or how fast the object is already moving. The third law ensures that every interaction respects perfect symmetry, with action and reaction always balanced. These symmetries have profound implications for how we understand conservation principles in nature. When the laws of physics remain unchanged as time passes, energy must be conserved. When they remain unchanged as you move from place to place, momentum must be conserved. When they remain unchanged as you rotate your experimental apparatus, angular momentum must be conserved. These conservation laws, implicit in Newton's framework but fully developed by later generations of physicists, govern every process in the universe from the smallest atomic interactions to the largest cosmic phenomena. Consider how conservation of angular momentum manifests in the world around you. When an ice skater pulls in their arms during a spin, they rotate faster because their angular momentum must remain constant. The same principle governs the formation of galaxies from rotating clouds of gas and dust. As these clouds collapse under their own gravity, they spin faster and faster, eventually flattening into the beautiful spiral structures we observe throughout the universe. This connection between earthly experience and cosmic phenomena reflects the deep unity that Newton's laws revealed. The physics governing a child's spinning top are identical to those shaping the rotation of entire galaxies. The mathematical relationships describing a dancer's pirouette also determine how fast pulsars spin as they emit their lighthouse beams of radiation across interstellar space. But Newton's framework reveals something even more profound about the nature of prediction and causality. His laws don't just describe what happens. They allow us to calculate what will happen, given sufficient information about current conditions. This predictive power transforms our relationship with the natural world from passive observation to active understanding. Think about the extraordinary precision this enables. Astronomers can predict exactly when and where solar eclipses will occur centuries into the future. Engineers can calculate precisely how much force a bridge must withstand before they begin construction. Mission planners can determine the exact trajectory a spacecraft must follow to reach Jupiter's moons, accounting for the gravitational influences of every major body in the solar system. This predictive capability extends to scales both vast and minute. Meteorologists use Newton's laws, combined with thermodynamics and fluid dynamics, to forecast weather patterns days in advance. The same mathematical principles help climatologists understand how atmospheric circulation patterns will respond to changing conditions over decades and centuries. Ocean currents, tidal patterns, and seasonal variations all follow predictable cycles governed by the mechanical relationships Newton first articulated. Yet, perhaps most remarkably, Newton's laws also govern the intricate dance of molecules that makes life possible. Every protein folding in your cells, every enzyme catalyzing a chemical reaction, every ion moving across a cellular membrane follows the same fundamental principles of force and motion. The electrical impulses racing through your nervous system as you process these words are guided by electromagnetic forces that obey Newton's third law, creating action-reaction pairs at the molecular level. Consider the elegant mechanics involved in something as simple as your heartbeat. Specialized cardiac muscle cells contract in coordinated waves, creating pressure differences that drive blood through your circulatory system. The timing of these contractions is controlled by electrical signals that propagate through your heart tissue at precisely regulated speeds. Each aspect of this process, from the molecular motors that cause muscle fibers to shorten to the fluid dynamics of blood flow through your arteries, operates according to the mathematical relationships Newton discovered. This same mechanical precision governs how your brain processes information. When you see a beautiful sunset or hear a favorite piece of music, sensory signals travel along your neural pathways as electrical impulses moving at speeds determined by the physical properties of nerve fibers. These signals trigger chemical reactions at synapses, releasing neurotransmitter molecules that diffuse across tiny gaps, according to the same principles that govern the motion of gas molecules in the atmosphere. The fact that consciousness emerges from these mechanical processes represents one of the deepest mysteries in science. How does the dance of atoms and molecules, following Newton's laws with perfect precision, give rise to subjective experience, to thoughts and feelings and the sense of being a unified self? This question pushes at the boundaries of our current understanding, suggesting that there may be organizational principles or emergent properties that we don't yet fully comprehend. Yet even as we grapple with these profound mysteries, Newton's laws continue to provide the foundational framework for understanding how complex systems organize themselves. From the flocking behavior of birds to the synchronization of fireflies, from the formation of traffic patterns to the emergence of economic markets, we see examples of simple rules creating complex coordinated behaviors. These phenomena illustrate how Newton's laws, operating at the level of individual interactions, can generate patterns and structures that seem to transcend their mechanical origins. Each bird in a flock responds to the positions and movements of its nearest neighbors according to simple rules that can be understood in terms of forces and accelerations. Yet the collective result is the fluid, coordinated motion of the entire group, displaying an apparent intelligence that emerges from the mechanical interactions of individual members. This emergence of complexity from simplicity reflects a deep principle about how the universe organizes itself. Simple mathematical relationships, repeated and combined across multiple scales and contexts, create the rich tapestry of phenomena we observe in nature. Newton's laws provide the fundamental grammar from which the universe constructs its infinite variety of patterns and behaviors. The same principle applies to the formation of crystals, where individual atoms arrange themselves in precise geometric patterns determined by the balance of attractive and repulsive forces between them. It governs the development of weather systems, where countless air molecules following Newton's laws collectively create the swirling patterns of hurricanes and the organized circulation of jet streams. It shapes the evolution of ecosystems, where individual organisms responding to environmental forces create the complex webs of relationships that characterize biological communities. Newton's framework also illuminates the profound relationship between stability and change in natural systems. Many of the patterns we observe in nature represent equilibrium states where opposing forces balance each other perfectly. A spinning top remains upright because the gravitational force trying to tip it over is exactly balanced by the gyroscopic forces created by its rotation. A planet maintains a stable orbit because the gravitational force pulling it toward its star is perfectly matched by the centrifugal force created by its orbital motion. Yet these equilibrium states are often dynamic rather than static. The stability emerges from continuous motion and adjustment rather than from rigid fixity. Your body maintains its temperature through constant metabolic activity, continuously producing and dissipating heat to maintain thermal equilibrium with your environment. Ecosystems maintain their diversity through ongoing cycles of birth, growth, death, and renewal. Even apparently, solid objects like rocks and mountains are continuously changing, shaped by forces operating over geological timescales. This dynamic view of stability has profound implications for how we understand change and permanence in the natural world. What appears stable and unchanging may actually represent a delicate balance of forces that could shift dramatically if conditions change even slightly. What appears chaotic and unpredictable may actually follow deep patterns that become visible only when viewed from the appropriate temporal or spatial perspective. Newton's laws also reveal the intimate connection between energy and information in physical systems. Every time forces act to change the motion of objects, energy flows from one form to another, and information about the interaction propagates throughout the system. When two billiard balls collide, kinetic energy transfers between them, according to the precise mathematical relationships Newton described. But the collision also creates sound waves, heat, and tiny vibrations that carry information about the interaction to distant parts of the system. This flow of energy and information creates a kind of memory in physical systems, where the effects of past interactions continue to influence future behavior. The current state of any system reflects its entire history of interactions, encoded in the positions, velocities, and internal states of all its components. This historical dimension of physical systems suggests that the universe possesses a kind of memory, preserving information about past events in the ongoing dance of matter and energy. Consider how this applies to the formation and evolution of cosmic structures. The distribution of galaxies we observe today reflects density fluctuations that existed in the early universe, amplified over billions of years by gravitational interactions governed by Newton's laws. The chemical composition of stars carries information about previous generations of stellar evolution, recorded in the relative abundances of different elements. Even the cosmic microwave background radiation preserves a fossil record of conditions in the universe when it was only a few 100,000 years old. This preservation of information through physical processes creates a kind of cosmic archaeology, where careful analysis of current conditions can reveal details about events that occurred billions of years in the past. The same principle applies to much smaller scales and shorter timescales. The rings in a tree trunk record variations in growing conditions year by year. The layers in sedimentary rocks preserve information about ancient environmental conditions. Even the wear patterns on a piece of machinery can reveal details about how forces have acted on it over time. Newton's laws thus provide not just a framework for predicting future behavior, but also tools for reconstructing past events from present evidence. This forensic aspect of physics has applications ranging from criminal investigations to archaeological research to understanding the evolution of the universe itself. In each case, careful analysis of how forces have acted on physical systems allows us to trace backward through time, reconstructing the sequence of events that led to current conditions. The mathematical precision of Newton's laws also enables a kind of dialogue between theory and experiment that continues to drive scientific progress. Each new measurement tests theoretical predictions with ever greater accuracy, either confirming our understanding or revealing phenomena that require deeper investigation. This ongoing conversation between mathematical theory and empirical observation has led to discoveries that Newton could never have imagined, from the quantum behavior of atoms to the relativistic effects of high-speed motion. Yet even as our understanding has expanded into these exotic realms, Newton's laws remain the foundation upon which more advanced theories are built. Einstein's relativity reduces to Newton's mechanics when velocities are much smaller than the speed of light and gravitational fields are relatively weak. Quantum mechanics incorporates classical concepts of momentum and energy, modified by the probabilistic nature of quantum states. Even the most advanced theories of particle physics rely on conservation principles that emerge naturally from the symmetries implicit in Newton's framework. This continuity between classical and modern physics reflects something profound about the cumulative nature of scientific knowledge. Each new discovery doesn't replace previous understanding, but extends it into new domains, revealing deeper layers of the mathematical structure underlying physical reality. Newton's insights remain as relevant today as they were 3 centuries ago, providing the conceptual foundation for technologies and discoveries he could never have anticipated. As we reflect on the extraordinary scope and enduring relevance of Newton's contributions, we begin to appreciate how completely his work transformed humanity's relationship with the natural world. Before Newton, the behavior of physical systems seemed mysterious and unpredictable, governed by hidden forces and incomprehensible principles. After Newton, the same phenomena revealed themselves as expressions of elegant mathematical relationships that could be understood, analyzed, and applied to practical problems. This transformation from mystery to understanding represents one of the greatest intellectual achievements in human history. It demonstrates the power of mathematical reasoning to reveal the hidden order underlying apparent chaos, to find simple principles that explain complex phenomena, to discover universal laws that govern the behavior of everything from falling apples to orbiting planets. But perhaps most importantly, Newton's work established a template for scientific inquiry that continues to guide our exploration of the natural world. He showed that careful observation, mathematical analysis, and rigorous testing of predictions could unlock the deepest secrets of nature. He demonstrated that the universe operates according to comprehensible principles that human minds can discover and understand. This optimistic vision of human capability continues to inspire scientists and engineers today. Every time we launch a spacecraft to explore the outer planets, every time we design new materials with precisely tailored properties, every time we develop technologies that seemed impossible to previous generations, we're building on the foundation that Newton established. His laws don't just describe the motion of objects. They reveal the underlying rationality of the cosmos, the mathematical harmony that makes scientific understanding possible. As you sit here contemplating these profound truths, you're experiencing Newton's laws in countless ways. The gravitational force holding you in your chair, the electromagnetic forces binding the atoms of your body together, the mechanical processes that keep your heart beating and your lungs breathing all operate according to the mathematical principles he first articulated. You are not separate from the cosmic dance of forces and motions that Newton described. You are part of it, a temporary arrangement of matter and energy, following the same fundamental laws that guide the evolution of galaxies across billions of years. This perspective reveals something beautiful about our place in the universe. We are not outside observers studying a foreign system. We are participants in the cosmic story, made from the same materials, governed by the same laws, connected to every other part of the universe through the invisible threads of force and motion that Newton first learned to describe mathematically. In understanding his laws, we understand something essential about ourselves and our relationship to the magnificent, mathematically ordered cosmos we call home. The gentle rhythm of your breathing, the steady beating of your heart, the quiet, electrical activity of your thoughts, all these processes unfold according to the same elegant principles that govern the motion of planets and the dance of galaxies. As you drift towards sleep, carried by these natural rhythms, you can rest in the knowledge that you're cradled by forces that Newton first revealed to human understanding, part of a universe whose deepest secrets yield to patient observation and mathematical insight. In Newton's vision, we glimpse not just the mechanics of motion, but the underlying harmony that makes existence itself possible. His laws reveal a cosmos where every action has consequences, where every force finds its balance, where the dance of matter and energy unfolds according to mathematical relationships of breathtaking elegance and precision. This is the world Newton saw when he watched that apple fall, and it's the same world that holds and sustains you in this quiet moment of contemplation. The mathematical beauty of Newton's work extends even deeper when we consider how these laws emerge from the fundamental structure of space and time themselves. Picture the universe as a vast stage where every interaction, every motion, every force follows the same underlying choreography. Newton didn't just discover rules that happened to work in his time and place. He uncovered principles so fundamental they operate at every scale, in every corner of the cosmos, across all of time. Consider what happens when you gently push a book across your desk. That simple action demonstrates all three of Newton's laws working in perfect harmony. The book resists your initial push, displaying inertia as described by the first law. When you apply force, the book accelerates according to the precise mathematical relationship of the second law. And as you push forward on the book pushes back against your hand with equal force, illustrating the third law's perfect symmetry. But here's what makes this truly extraordinary. The same mathematical relationships governing that book on your desk also determine how spacecraft navigate between planets, how electrons orbit atomic nuclei, and how galaxies spiral through the cosmic web. The force you applied to move the book follows the same principles that shape the large-scale structure of the universe itself. This universality reveals something profound about the nature of mathematical truth. Newton's equations aren't just convenient approximations or useful models. They describe something fundamental about how reality operates. When mathematicians work with these equations today, they're manipulating the same abstract relationships that govern the physical behavior of every piece of matter in the observable universe. Think about the elegant precision involved in something as commonplace as walking. Each step you take requires your brain to calculate, largely unconsciously, the exact forces needed to lift your leg, swing it forward, and place your foot at precisely the right location to maintain balance. Your muscles apply forces that accelerate your limbs according to Newton's second law. Your foot pushes against the ground, and the ground pushes back with equal force, propelling you forward in accordance with the third law. This biological application of Newtonian mechanics extends to every living creature. A bird in flight continuously adjusts the angle and motion of its wings, creating pressure differences that generate lift forces perfectly calibrated to support its weight. A fish swimming through water uses its fins to create action-reaction pairs that propel it through the liquid medium. Even plants, though they appear static, constantly adjust their growth patterns in response to gravitational forces, orienting their roots downward and their leaves towards sunlight. The mathematical framework Newton established also illuminates the relationship between order and chaos in natural systems. Many phenomena that appear random or unpredictable actually follow deterministic rules based on his laws. Weather patterns, though complex and difficult to forecast far into the future, emerge from the mechanical interactions of countless air molecules, each obeying Newton's principles of motion and force. Consider how this applies to the formation of river systems. Water flows downhill under the influence of gravity, following the path of least resistance as it carves channels through the landscape. Yet the resulting network of streams and tributaries displays fractal patterns of remarkable complexity and beauty. The same mathematical relationships that describe a single water droplet rolling down a slope also govern the branching structure of entire river systems spanning thousands of square miles. This emergence of complex patterns from simple rules reflects a deep principle about how the universe organizes itself. Individual interactions, each following Newton's laws with mechanical precision, combine to create structures and behaviors that seem to transcend their purely physical origins. A flock of starlings wheeling through the sky displays an apparent intelligence and coordination that emerges from each bird, simply responding to the positions and movements of its nearest neighbors. The same principle operates in human-made systems. Traffic flows through city streets according to patterns that can be understood using the mathematical tools Newton developed. Each driver makes individual decisions based on local conditions, yet the collective result often displays predictable statistical properties. Engineers use modified versions of Newton's equations to model traffic flow, optimize signal timing, and design road networks that minimize congestion. Newton's insights also reveal the profound connection between symmetry and physical law. His equations remain unchanged whether you're moving north or south, whether you perform your experiments on Earth or Mars, whether you conduct them today or 1,000 years from now. This mathematical symmetry isn't merely convenient for scientists. It reflects something fundamental about the structure of reality itself. This principle of symmetry has far-reaching implications for our understanding of conservation laws in nature. When the laws of physics remain unchanged as time passes, energy must be conserved throughout the universe. When they remain unchanged as you move from place to place, momentum must be conserved in every interaction. These conservation principles, which emerge naturally from the symmetries in Newton's framework, govern processes ranging from the collision of subatomic particles to the merger of galaxy clusters. Think about how conservation of momentum manifests in your daily experience. When you catch a baseball, your hands and the ball exert equal and opposite forces on each other during the brief moment of contact. The ball's momentum decreases as yours increases by exactly the same amount. The total momentum of the system remains perfectly constant, even though the ball comes to rest in your glove while you recoil slightly backward. This same principle governs interactions at every scale. When two galaxies pass close to each other, their gravitational interaction can dramatically alter both their shapes and trajectories, but the total momentum of the system remains unchanged. When a supernova explosion hurls stellar material outward at tremendous velocities, the remaining neutron star recoils in the opposite direction with precisely the momentum needed to balance the equation. The mathematical precision of these conservation laws enables remarkably accurate predictions about complex systems. Astronomers can calculate the orbital mechanics of binary star systems, accounting for how gravitational interactions gradually change the star's paths over millions of years. Engineers can design collision avoidance systems for spacecraft, predicting exactly how gravitational encounters with planets will alter a probe's trajectory. Newton's framework also illuminates the relationship between force and energy in ways that continue to guide modern technology. When you wind up a mechanical clock, you're storing energy in the spring by applying force through a distance. This stored energy is then released gradually as the spring unwinds, powering the clock's mechanism through precisely regulated motion. The mathematical relationships Newton described govern every aspect of this process, from the elastic properties of the spring to the pendulum's oscillation frequency. Consider how this principle applies to renewable energy systems. Wind turbines extract kinetic energy from moving air masses, converting the linear motion of wind into rotational motion that generates electricity. Solar panels convert electromagnetic radiation directly into electrical energy, but the mounting systems that orient them toward the sun rely on mechanical systems governed by Newton's laws. Hydroelectric generators harness the gravitational potential energy of elevated water, transforming it into electrical power through precisely engineered turbine systems. Each of these technologies represents a practical application of the mathematical relationships Newton first articulated. The efficiency of a wind turbine depends on the precise balance between the aerodynamic forces acting on its blades and the mechanical forces resisting their rotation. The stability of a solar panel array requires careful analysis of how wind loads will be transmitted through the support structure. The design of a hydroelectric dam must account for the enormous forces created by millions of tons of water pressing against the barrier. The universality of Newton's laws also becomes apparent when we consider how they govern the behavior of matter at the molecular level. The proteins in your body maintain their complex three-dimensional shapes through delicate balances of electromagnetic forces acting between individual atoms. When these proteins change shape to perform their biological functions, they're following the same mechanical principles that govern the motion of planets around stars. Think about the remarkable precision involved in DNA replication. Molecular machines called polymerases move along DNA strands, reading the genetic code and assembling complementary strands with extraordinary accuracy. Each step in this process involves forces acting on individual molecules, accelerating them through tiny distances according to Newton's second law. The energy required for these molecular motions comes from chemical reactions that store and release energy through the formation and breaking of atomic bonds. This molecular choreography extends to every biological process. When your muscles contract, billions of protein filaments slide past each other, creating macroscopic motion through the coordinated action of countless microscopic force-generating systems. When your heart beats, electrical signals trigger precisely timed contractions in cardiac muscle cells, creating pressure waves that propagate through your circulatory system according to the principles of fluid mechanics that Newton helped establish. The mathematical tools Newton developed for analyzing motion and force have also proven essential for understanding how complex systems maintain stability in the face of constant change. Your body temperature remains remarkably constant despite wide variations in environmental conditions and internal heat production. This stability emerges from feedback mechanisms that continuously adjust heat production and heat loss, maintaining thermal equilibrium through processes that can be analyzed using the mathematical framework Newton established. Consider how this principle applies to ecological systems. Forest ecosystems maintain their diversity and stability through complex networks of interactions between species, each relationship involving flows of energy and materials that follow fundamental physical principles. Predator-prey relationships create oscillating population dynamics that can be modeled using modified versions of the mathematical tools Newton developed for analyzing periodic motion. The same mathematical approaches help us understand economic systems where the flow of goods, services, and information creates patterns analogous to those seen in physical systems. Market dynamics often display the same kinds of oscillatory behavior seen in mechanical systems, with periods of growth and contraction that reflect the underlying forces of supply and demand operating on countless individual transactions. Newton's insights also illuminate the deep connection between information and physical processes. Every time forces act to change the motion of objects, information about the interaction propagates throughout the system. When you clap your hands together, the collision creates sound waves that carry information about the interaction to distant parts of your environment. The acoustic energy spreads outward according to the same mathematical principles that govern the propagation of other forms of information through physical media. This information-carrying capacity of physical interactions has profound implications for how we understand communication and computation in natural systems. The electrical signals that carry information through your nervous system propagate at speeds determined by the physical properties of nerve fibers. The chemical signals that coordinate cellular activities diffuse through biological tissues according to the same principles that govern the motion of gas molecules in the atmosphere. Think about how this applies to the remarkable phenomenon of bird migration. Millions of birds navigate across thousands of miles, using information gathered from magnetic fields, star patterns, and landmark recognition. The mechanical principles governing their flight, from the aerodynamics of wing motion to the metabolic processes that power their journey, all follow the mathematical relationships Newton described. Yet somehow, these purely physical processes give rise to navigation capabilities that seem almost miraculous in their precision and reliability. The mathematical framework Newton established continues to guide our exploration of phenomena at the very largest scales of space and time. When astronomers observe the cosmic microwave background radiation, they're seeing light that has been traveling through space for nearly 14 billion years. The properties of this ancient light carry information about conditions in the early universe, encoded in patterns that can be analyzed using mathematical tools that trace their origins to Newton's work. Consider the elegant mechanics involved in gravitational lensing, where the curvature of space-time around massive objects bends the path of light from distant sources. While Einstein's general relativity provides the complete theoretical framework for understanding these effects, the basic principle follows naturally from Newton's insight that gravity affects all forms of matter and energy. The same gravitational forces that keep planets in orbit also deflect light rays, creating cosmic telescopes that allow us to observe galaxies billions of light years away. This connection between local and cosmic phenomena reflects the deep unity that Newton's laws revealed. The mathematical relationships governing motion in your immediate environment extend seamlessly to the largest structures in the observable universe. Galaxy clusters, containing thousands of individual galaxies spread across millions of light years, maintain their coherent structure through gravitational interactions that follow exactly the same principles as the forces holding together our solar system. The predictive power of Newton's framework also enables us to understand how cosmic structures evolve over timescales that dwarf human experience. Computer simulations can model the formation and evolution of galaxy clusters over billions of years, tracking how dark matter halos collapse under their own gravity and how ordinary matter follows these invisible scaffolds to create the luminous structures we observe today. These simulations require enormous computational resources, but they're based on the same fundamental equations Newton first wrote down centuries ago. Each simulated particle follows a trajectory determined by the gravitational forces exerted by all the other particles in the system, integrated forward through time using numerical methods that preserve the mathematical relationships Newton discovered. The results of these calculations reveal a universe of extraordinary complexity and beauty, where simple physical laws give rise to intricate cosmic architectures. Filaments of dark matter stretch across hundreds of millions of light-years, connected by nodes where galaxy clusters form. Vast voids, nearly empty of matter, separate these cosmic structures. The entire pattern resembles a three-dimensional web of incredible delicacy and grandeur. Yet all of this cosmic complexity emerges from the operation of forces and motions that Newton first learned to describe mathematically. The same principles that govern a child's spinning top also determine how galaxy clusters rotate and evolve over cosmic time. The mathematical relationships that describe a pendulum's oscillation also govern the orbital dance of binary stars as they spiral toward eventual merger. This universality of physical law continues to inspire scientists and philosophers as they contemplate the deepest questions about the nature of reality. Why should the universe be comprehensible to mathematical analysis? Why do simple equations describe complex phenomena with such extraordinary precision? These questions point towards something profound about the relationship between human reasoning and the cosmic order. Newton himself was deeply aware of these philosophical implications. He saw his mathematical description of natural phenomena as revealing the rational structure underlying creation itself. The elegance and universality of his laws suggested to him that the universe operates according to a divine plan, implemented through mathematical principles of perfect consistency and beauty. Whether or not one shares Newton's theological interpretation, the mathematical harmony he discovered continues to evoke wonder and amazement. The fact that human minds, evolved on a small planet orbiting an ordinary star, can discover mathematical relationships that govern the behavior of matter and energy throughout the cosmos remains one of the most remarkable features of our existence. This capacity for mathematical understanding also enables us to participate consciously in the cosmic processes that Newton first described. When engineers design spacecraft trajectories that take advantage of gravitational assists from planets, they're using human intelligence to navigate through the same force fields that have guided the motion of celestial bodies for billions of years. When architects design buildings that can withstand earthquakes and hurricanes, they're applying mathematical principles to create structures that work in harmony with natural forces rather than in opposition to them. The practical applications of Newton's insights continue to expand as our technological capabilities advance. Precision manufacturing relies on extremely accurate control of mechanical forces to create components with tolerances measured in fractions of micrometers. Medical devices use sophisticated mechanical systems to perform minimally invasive surgeries with extraordinary precision. Transportation systems, from automobiles to aircraft to spacecraft, all depend on engineering applications of the mathematical relationships Newton established. Yet perhaps the most profound legacy of Newton's work lies not in any specific technological application, but in the demonstration that the natural world operates according to comprehensible mathematical principles. This insight transformed humanity's relationship with nature from one of superstition and mystery to one of understanding and partnership. It showed that careful observation, mathematical analysis, and rigorous testing could unlock secrets that had remained hidden for millennia. The optimistic vision of human capability that Newton's work represents continues to guide scientific inquiry today. Every time researchers discover new particles at accelerator facilities, every time astronomers detect gravitational waves from colliding black holes, every time engineers develop new materials with precisely tailored properties, they're building on the foundation of mathematical understanding that Newton established. This cumulative nature of scientific knowledge reflects something beautiful about human civilization. Each generation builds upon the insights of those who came before, extending understanding into new territories while preserving the essential truths earlier generations discovered. Newton himself acknowledged this continuity, famously writing that if he had seen farther than others, it was by standing on the shoulders of giants. The giants Newton stood upon included not only earlier scientists and mathematicians, but also the countless unnamed individuals who developed the intellectual tools that made his synthesis possible. The mathematical notation he used, the experimental techniques he employed, the logical methods he applied, all emerged from centuries of human intellectual development. His achievement was to combine these tools in new ways, creating a theoretical framework of unprecedented power and generality. This collaborative aspect of scientific progress continues today as researchers around the world contribute to our understanding of natural phenomena. The mathematical language Newton helped establish enables scientists from different cultures and backgrounds to communicate their discoveries and build upon each other's work. The universality of his laws provides a common foundation that transcends national boundaries and cultural differences. As you contemplate these profound connections between mathematical truth and physical reality, you're participating in the same kind of intellectual adventure that drove Newton to his revolutionary insights. The capacity for wonder, the desire to understand, the ability to see patterns and relationships in natural phenomena. These are the same human qualities that enabled Newton to transform our understanding of the cosmos. The mathematical relationships he discovered continue to operate around you at every moment. The gravitational forces holding you in your chair, the electromagnetic interactions binding the atoms of your body together, the mechanical processes that keep your heart beating steadily, all follow the same elegant principles that govern the motion of planets and the evolution of galaxies. In understanding Newton's laws, you gain insight not just into the mechanics of motion, but into the fundamental rationality of the universe itself. You discover that you live in a cosmos where every action has consequences, where every force finds its balance, where the dance of matter and energy unfolds according to mathematical relationships of breathtaking precision and beauty. This knowledge connects you to something larger than yourself, to the grand story of cosmic evolution that began with the first stirrings of matter and energy billions of years ago and continues today in the quiet rhythm of your breathing, the steady beating of your heart, the gentle electrical activity of your thoughts. You are not separate from the universe Newton described. You are part of it, a temporary arrangement of stardust and space-time, held together by forces that operate with mathematical precision across all scales of existence. As the gentle pull of sleep draws you deeper into contemplation, you can rest in the knowledge that you're cradled by the same elegant laws that guide comets in their orbits and hold galaxies in their majestic spiral patterns. Newton's vision reveals a universe where order emerges from apparent chaos, where simple principles generate infinite complexity, where human minds can discover mathematical truths that illuminate the deepest structures of reality itself. The story of how one man looked at a falling apple and saw the invisible threads connecting all matter and energy throughout the cosmos remains one of the greatest intellectual achievements in human history. But it's also your story, because those same threads of force and motion that Newton first learned to describe mathematically continue to weave the fabric of your existence, connecting you intimately to the magnificent, mathematically ordered universe you call home. In the quiet moments before sleep carries you away, consider the extraordinary journey we've taken together through Isaac Newton's revolutionary understanding of motion and force. We've traced the arc from a falling apple to the cosmic dance of galaxies, discovering how three elegant laws reveal the mathematical harmony underlying all of existence. Tonight, as you rest, you carry with you the profound realization that you are intimately connected to every star in the night sky, every planet in distant solar systems, every particle of matter throughout the observable universe. The same gravitational force that gently holds you against your bed extends across billions of light years, shaping the large-scale structure of the cosmos itself. Think about the beautiful simplicity of what Newton discovered. Objects at rest stay at rest. Objects in motion stay in motion, unless acted upon by external forces. This first law reveals that motion is the natural state of matter, that stillness and movement are both expressions of the same underlying principle. Your body, seemingly at rest, is actually racing through space at tremendous velocities as Earth spins, orbits the Sun, and travels with our galaxy through the cosmic web. The second law shows us that every acceleration, every change in motion throughout the universe follows the precise mathematical relationship between force, mass, and acceleration, from the gentle flutter of a butterfly's wings to the collision of neutron stars, from the electrical impulses in your nervous system to the nuclear fusion burning in stellar cores. Every interaction obeys this same fundamental equation. And the third law reveals the profound interconnectedness of all things, showing us that forces always come in pairs, that every action creates an equal and opposite reaction. When you breathe, you push against the air, and the air pushes back, filling your lungs with the oxygen that sustains your life. When your heart beats, it creates pressure waves that travel through your circulatory system, carrying nutrients and energy to every cell in your body. These aren't just abstract principles confined to physics textbooks. They are the living reality of your existence, the mathematical poetry that describes how matter and energy dance together to create the rich tapestry of experience we call life. Every sensation you feel, every thought you think, every emotion you experience emerges from the elegant interplay of forces that Newton first learned to describe with mathematical precision. As you drift towards sleep, carried by the natural rhythms of your body, remember that you are witnessing Newton's laws in their most intimate expression. Your breathing follows the mechanical principles of pressure and volume. Your heartbeat demonstrates the conversion of chemical energy into mechanical motion. Your brain processes information through electrical signals that propagate according to the same principles governing lightning bolts and solar flares. The mathematical relationships Newton discovered don't just describe the world around you. They reveal something profound about the nature of understanding itself. They show us that the universe operates according to comprehensible principles, that human minds can discover eternal truths about the structure of reality, that careful observation and mathematical reasoning can unlock secrets that have remained hidden since the beginning of time. This capacity for understanding connects you to a tradition of inquiry that stretches back through countless generations of curious minds. Every person who has ever wondered why objects fall, why planets move in irregular patterns, why the natural world displays such remarkable order and predictability, has been asking the same fundamental questions that drove Newton to his revolutionary insights. The tools he developed to answer these questions continue to guide our exploration of phenomena he could never have imagined. The spacecraft exploring the outer reaches of our solar system navigate through gravitational fields using calculations based on his equations. The satellites that enable global communication maintain their orbits through applications of his laws of motion. The technologies that power our modern civilization, from electricity generation to transportation systems to medical devices, all rely on engineering applications of the mathematical framework he established. Yet perhaps the most remarkable aspect of Newton's legacy lies not in any specific technological achievement, but in the profound shift in human perspective his work created. Before Newton, the natural world seemed mysterious and unpredictable. governed by hidden forces that operated according to incomprehensible principles. After Newton, the same phenomena revealed themselves as expressions of elegant mathematical relationships that could be understood, analyzed, and applied to practical problems. This transformation from mystery to understanding represents one of the greatest intellectual achievements in human history. It demonstrates the power of mathematical thinking to reveal the hidden order underlying apparent chaos, to find simple principles that explain complex phenomena, to discover universal laws that govern the behavior of everything from subatomic particles to galaxy clusters. The universe Newton revealed is not a collection of separate objects moving through empty space, but a unified system where every part influences every other part through invisible threads of force and motion. When you move your hand, that action creates gravitational waves that propagate throughout the cosmos, carrying information about your motion to the most distant galaxies. The effect is infinitesimally small, but it is real, demonstrating the fundamental interconnectedness of all matter and energy. This interconnectedness extends through every scale of existence. The atoms in your body were forged in the nuclear furnaces of ancient stars, scattered into space by supernova explosions, and gathered again by gravitational forces into the planets where life could emerge and evolve. The calcium in your bones, the iron in your blood, the carbon in your DNA, all participated in cosmic processes that unfolded over billions of years according to the same mathematical principles Newton first articulated. The water molecules flowing through your circulatory system have been cycling through Earth's environment for geological ages, falling as rain, flowing in rivers, evaporating from oceans, condensing in clouds, participating in countless biological and geological processes. Each molecule carries with it a history written in the language of forces and motions, a story of interactions that spans the entire history of our planet. Even the energy powering your thoughts originated in nuclear reactions deep within the sun, where hydrogen atoms fuse to form helium under conditions of temperature and pressure that would be impossible to recreate on Earth. This energy traveled across 93 million miles of space as electromagnetic radiation, was captured by plants through photosynthesis, flowed through food webs, and eventually reached your brain where it powers the electrical activity of consciousness itself. The mathematical precision with which these processes unfold reveals something extraordinary about the architecture of reality. The universe doesn't just happen to follow mathematical patterns. It seems to be constructed from mathematical relationships, as if numbers and equations are the fundamental building blocks from which all physical phenomena emerge. This mathematical nature of reality continues to astonish scientists and philosophers. Why should the universe be comprehensible to mathematical analysis? Why do simple equations describe complex phenomena with such extraordinary precision? These questions point towards something profound about the relationship between human reasoning and the cosmic order, suggesting that our capacity for mathematical understanding reflects something fundamental about the structure of existence itself. Newton's work also reveals the cumulative nature of human knowledge, showing how each generation builds upon the insights of those who came before. The mathematical tools he developed grew out of centuries of intellectual development, combining insights from geometry, algebra, and the emerging field of calculus into a unified framework for understanding motion and force. This collaborative aspect of scientific progress continues today as researchers around the world contribute to our understanding of natural phenomena. The discoveries being made at particle accelerators, space telescopes, and research laboratories everywhere build upon the foundation Newton established, extending our knowledge into realms he could never have imagined, while preserving the essential truths he uncovered. The optimistic vision of human capability that Newton's work represents continues to inspire new generations of scientists, engineers, and curious minds. It shows us that no mystery is too deep to be understood, no phenomenon too complex to be analyzed, no question too fundamental to be answered through careful observation and mathematical reasoning. As you settle into the embrace of sleep, carried by the gentle rhythms that have sustained life for billions of years, you can rest in the knowledge that you are part of something magnificent and comprehensible. The forces that hold you, the motions that sustain you, the energy that animates you, all follow mathematical relationships of breathtaking elegance and precision. The universe Newton revealed is not a cold mechanical system indifferent to human concerns, but a cosmos of extraordinary beauty and harmony, where conscious beings can discover their place in the grand scheme of existence. In understanding his laws, you gain insight into your own nature as a temporary arrangement of matter and energy that has somehow achieved the remarkable feat of self-awareness. This awareness connects you to the deepest mysteries of existence while grounding you in the solid foundation of mathematical truth. You are both an observer of the cosmic dance and a participant in it, both a student of natural law and an expression of it, both a seeker of understanding and a manifestation of the universe's capacity to understand itself. The gentle weight of sleep drawing you deeper into rest is itself an expression of Newton's laws, as your body responds to the gravitational forces that have shaped the structure of space and time since the beginning of the universe. Your breathing slows according to the same mechanical principles that govern the oscillation of pendulums and the orbital periods of planets. In these quiet moments, as consciousness fades into the peaceful darkness of sleep, you embody the profound truth that Newton's laws revealed. You are not separate from the universe, but intimately connected to it, held by the same forces that guide comets in their orbits and galaxies in their stately dance across cosmic time. Tonight, as the quietness settles around you and your thoughts begin to drift like particles following their natural trajectories, remember that Isaac Newton's greatest gift to humanity wasn't just the discovery of these three profound laws. It was the revelation that the universe speaks to us in the language of mathematics, that beneath the apparent complexity of existence lies an elegant simplicity waiting to be understood. In those final moments before sleep takes hold, consider the extraordinary privilege of being conscious in a cosmos governed by such beautiful principles. You are stardust that learned to think, matter that became aware of its own motion, a temporary eddy in the cosmic flow that has achieved the remarkable ability to comprehend the very forces that created it. The apple that fell in Newton's garden 3 centuries ago continues to fall, in a sense, through every generation that rediscovers the wonder of understanding how the universe works. Tonight, you've joined that endless procession of curious minds, carrying forward the flame of inquiry that transforms mystery into knowledge, chaos into order, ignorance into insight. As your eyes grow heavy and your breathing deepens into the rhythm of rest, know that you're experiencing Newton's laws in their most intimate form. Your body settles into equilibrium, forces balancing perfectly as you surrender to the gravitational embrace that connects you to every other piece of matter in the observable universe. The same mathematical relationships that describe the motion of distant galaxies also govern the gentle rise and fall of your chest, the steady circulation of blood through your veins, the electrical patterns of dreams beginning to form in your sleeping mind. You are both subject to these laws and a living expression of their profound beauty, a conscious participant in the cosmic symphony that Newton first learned to hear. Rest now in the knowledge that you understand something eternal about the nature of reality itself. The forces that cradle you as you sleep are the same forces that have shaped the evolution of stars, the formation of planets, and the emergence of life throughout the cosmos. In Newton's vision, you glimpse not just the mechanics of motion, but the underlying harmony that makes existence itself possible. Sweet dreams, fellow traveler in this mathematically ordered universe. The cosmic dance continues around you and through you, each moment unfolding according to principles of breathtaking elegance and precision. And in understanding these principles, even briefly, you touch something timeless about the magnificent, interconnected whole we call home. Thank you for joining me on this gentle journey through Isaac Newton's revolutionary insights. Until we meet again in another exploration of the wonders that surround us, may your curiosity remain boundless and your sense of wonder never fade. The universe has so much more to reveal, and minds like yours are exactly what it needs to unlock its remaining secrets. Have a good night. This is Boring Science signing off. Cheers.